Tonight we'll be hearing from George Matsumoto, who is Senior Education and Research Specialist at the Monterey Bay Aquarium Research Institute. For all of you who've joined us previously at our Monterey Bay events, I'm sure George will be a familiar face for you. Anyone who hasn't met him, I'm thrilled that you can meet him. So with that, we can start with George.
So my name is George Matsumoto. I am the Senior Education and Research Specialist at the Monterey Bay Aquarium Research Institute. I've been there for 23 years now, so a little while. I'm a California native, third generation. I grew up down in Southern California and pretty much always knew ever since 5th grade that I was interested in the ocean and that I wanted to study the ocean. I didn't tell my parents until I had finished college that I wasn't going to go their career path, which was to take over my dad's medical career office. So that was a fairly lengthy discussion that we had. And it's really their fault because they're the ones who signed me up for an outdoor adventure when I was in 5th grade that took me out to Anacapa Island, one of the Northern Channel Islands, for a weekend of camping and snorkeling, which was the first time I'd ever put a mask and snorkel on and looked under the surface of the ocean. And that just opened up a whole new world for me and sort of led me down the path I ended up on. So I went to undergraduate at UC Berkeley. At that time, I'm old enough that nothing was computerized, so college catalogs you could only find in the College Career Center. And I couldn't be bothered to really look through it. So I chose UC Berkeley mostly because it gave me a chance to get away from home. I got to UC Berkeley and I quickly found out that they did not have a marine biology program. So that was a minor problem. They had a marine botany program. So I became a marine botany major. So my initial training is as a phycologist, somebody who studies seaweeds. That's what I spent 4 years doing. After college, I took a year off, mostly trying to get up the nerve to tell my parents that I was not going to go to medical school. And I came back down to Southern California and I worked on Catalina Island for 6 months. And at the end of that, I ended up taking the GREs, the graduate record exams. I also took the MCATs, the medical college admission tests. And I did well on both. And I told my parents at that point that I was not going to go to medical school. And they were very reluctant about my career path, but it turned out that I was able to find a funded graduate program at UCLA, so they did not have to support me. So that kind of made the decision process my own, which is very nice. I did end up back in Los Angeles, and I did end up living with my parents for the first year, so they did have to support me a little bit, I guess. But I got my PhD from UCLA. I came back up here to the Monterey area and I did the last 2 years of my PhD work working for MBARI in 1989 and 1990, just as MBARI was getting started. And then I did a postdoctoral fellowship at Hopkins Marine Station with Stanford University. And then I went down to Australia where I spent 3 years setting up a marine biology program in a marine biology lab before coming back to Monterey, where I've been ever since. And my research is on the deep sea. And the picture you see here is the Monterey Bay Aquarium Research Institute in Moss Landing, California. It is a picture taken by a kayaker. Their whales are really, really close to shore. This was taken 4 years ago when we had an incredible bloom of bait fish. And for 10 weeks, we had whales feeding. You could swim out to them. They were that close to the beach. So it really was amazing. And the reason they're that close is because that's where the Monterey Submarine Canyon starts and the entrance to the deep sea. So the Monterey Submarine Canyon is the largest submarine canyon on the west coast of North America. It stretches down 4,000 meters by the time you get about 60 kilometers offshore. And accessing the deep sea has really been the problem historically. Using nets only gives you a small subsample. You miss out on all the delicate animals you see off to the sides of this picture. We can't spend much time in the deep sea either, so it's really been a problem. Even if you go down in a human-occupied vehicle like Alvin, the depth is limited. Their current depth right now is 5,000 meters. The average depth of the world ocean is 4,000 meters. The deepest spot is over 11,000 meters. So human-occupied vehicles don't get us all the way down to the bottom, although there are a couple now that could reach all the way down there. Human-occupied vehicles are also really expensive. And so David Packard, when he started up the Monterey Bay Aquarium Research Institute, decided to devote our focus towards remotely operated vehicles. So these are robots that we send down and we get to stay on board the surface ship, controlling what they see and what they do. His vision really focused on creating partnerships between scientists and engineers. And what Evan and Marie were talking about in terms of system engineering is exactly what we do at MBARI, only we also integrate scientists into the equation. And it's really critical, this teamwork aspect. And if I was looking at trying to highlight any sort of job skills or knowledge needed to succeed, it is teamwork. And I know from firsthand that students generally don't like to work in groups. They don't like to work in teams because they always feel that somebody isn't pulling their weight or somebody's not paying attention. But teamwork is critical. It's really hard to succeed in almost any field working in a vacuum, working all by yourself. And so any effort to get students to work together in groups of any size is, I think, a good advantage for them in the future. At MBARI, we also insist heavily on data management. What we learn is no good if we can't archive it and share it with others. And so we do a lot of work focusing on how we use data. Just to give you an overview of where we are, Moss Landing is right here, Santa Cruz is up at the top, Monterey is down at the bottom. And if there's any teachers who are not in California, we're about 2 hours south of San Francisco and about 5 hours north from Los Angeles. So that's sort of where we're located. And the MBARI way, as I said before, is to really use the systems and engineering approach to solving all of our problems. And the idea is that good systems engineering will lead to solutions and often lead to unanticipated discoveries and new opportunities. And one of David Packard's sayings that we really enjoy is that we need to go long and be willing to take risks. Another way of looking at it is if you don't make a mistake, we're not trying hard enough. And that's good because we make mistakes. Life is not perfect, as both the other speakers talked about. The advantage of working at MBARI is that we're not only allowed to make mistakes, we're often encouraged because it shows that we're doing something risky. We're trying something that other people can't do and haven't even tried to do yet because it is risky. And so it really is a wonderful place to work. We really enjoy it. My specific research focuses in on jellies primarily, but I'm also interested in how the inhabitants of the ocean are reacting to the changes that we're coming up with. And the ocean is really changing rapidly, both in terms of chemistry and biology. And MBARI is trying to not only keep track of those changes, but also to anticipate how the ocean is going to react to changes in the future. So we're trying to model out 10, 20, 50 years in the future and get an idea of what the ocean is going to look like that far in advance. And our overall goals are to essentially develop locally and share globally. We want to try to ask questions that other people can't ask and try to answer those questions using our local expertise and knowledge. And whatever we develop, we want to share with everybody else. And so we're very fortunate that we are privately funded. And so we're not in the business of making money. We don't try to develop patents and then make people pay for what we've developed, which would much rather share everything that we do with as many people as we can. And so again, these are all things that make MBARI a really pleasurable place to work. And we do enjoy it. Our major research priorities are to take the laboratory into the ocean. We don't really want to spend time working in the lab when we have this incredible environment right outside of our door. We want to spend as much time as possible in the ocean. We want to target samples. We really want to focus our sampling on specific things. We know we can't do everything, so we're really going to try to target the things that we think we could be good at. And we want to be in the ocean as much as possible. So where we can, we want to be there 24 hours a day, 365 days a year, and for multiple years. And as you can imagine, that creates an enormous issue with data, because that means there's an equivalent amount of data that has to be processed and worked with, which sort of leads me to where I'm looking for help from teachers, because I want you to help me figure out what we could do with all of that data. And so I put all these links into the chat box as well, but I just want to talk about a couple of different opportunities that we have, a couple of different things that MBARI has been developing. One is our teacher professional development workshop that's called Earth. Earth, the focus is to try to get real data into the classrooms. We don't bring you to a workshop and then give you a bunch of pre-developed lesson plans, because we're not curriculum specialists, we're scientists and engineers. We could gather data, but what we want is your help in taking that data and turning it into the lesson plans. And that's what Earth has been doing now for 16 years. We've been running these workshops all around the United States. The Earth 2021 workshop will be in Dobbs Ferry, New York, and it'll focus in on a number of different topics, including virtual reality and soundscape, the sounds of the ocean, as well as some of the data coming back from profiling floats that we're starting to launch in the world ocean. And that's the next step, adopting a float. MBARI is part of a much larger program called SOCOM, the Southern Ocean Climate Observations and Modeling Program. And as part of that, we've been launching floats into the Southern Ocean, about 30 floats a year. And for the last 3 years, we've been getting all those floats adopted by different school groups and different, sometimes homeschool groups, or even sometimes just some interested individuals or families can adopt a float. And once you've adopted a float, you get ownership of the float, so to speak. That name goes into the database that will live on forever. The float stays out to sea for up to 5 years. And I'll show you a little animation of how that float works. And then we also started to produce a list of some resources that we felt might be helpful to you at home. So that URL is also down there on that list. And oceanographers and polar scientists in specific really get to do all kinds of neat field work. And this is something that intrigued me a lot when I was growing up, the chance to spend time in the field. In reality, you might spend a little bit of time in the field, but a lot of your time is spent in front of a computer. So that may turn off some students into the field, but that's something important for them to know. Very few people get to spend their entire life out at sea, although we do need technicians who are willing to do that. Over time, the equipment has gotten fancier and fancier. In this picture, on the left-hand side is a reversing thermometer. This is how they used to measure the temperature at different places, at different layers in the ocean. They'd send this down, they'd take the temperature and then they'd flip it, which would lock in the temperature at a specific depth. Now we could send a profiling float down there to measure the temperature at 2,000 different data points over a 2,000 meter path. So we could get lots and lots of data, more data than ever before. And over the last 5 years, a large program called Argo has been going on. And Argo is a profiling float program that has been launching floats all around the world ocean. And these are just profiling floats. They go out into the ocean, you toss them over the side. On the left-hand side, you can see the basic size of them. They'll do 180 cycles. They'll do a cycle every 10 days. And what that means is they normally sit at 1,000 meters. On the 10th day, they'll go down to 2,000 meters. They'll come up to the surface, collecting data all the way up, and then send that data to a satellite, and then go back down to 1,000 meters. So they're just drifting. And there are thousands of these floats around the world. And MBARI, as a research organization, we're trying to add more sensors to that float package. We want more information than temperature, salinity, and location. So we're putting in what we call biogeochemical sensors, sensors that'll measure more of the biology and the geology and the chemistry of the water. And we're putting these on the same type of profiling floats, and we're starting to launch them all around the world. The ones in the Southern Ocean specific, this is just a little animation, provide data from the Southern Ocean. And this was really critical. This was an area that the Argo floats avoid. They don't go anywhere here down in the Southern Ocean because the water is usually considered to be too rough. But we decided that getting the data back was going to be worth the risk. And so we're risking frozen ice, we're risking icebergs, and we're risking the incredible wave energy that's down there, down in the Southern Ocean. But we're putting these floats down there. We've already launched over the last 5 years. We've put down about 150 floats, and they are collecting all kinds of different data while they're down there, and then sending that data back up to the satellite. And then those go right down into the internet, and they'll sit there ready for your students to access all that data. And all that data is available for anyone, anywhere in the world. It's all shared. So we don't archive any of it for our use. Everything we put out there goes out to the world as soon as possible. And this is sort of a look at the number of floats on the left-hand side. You can see Antarctica in the middle. All those floats you see are floats that have been launched in their paths around the Southern Ocean because they are drifting. On the right-hand side, you can see how students and teachers can access all that data. And if you could look really closely, you could see a bunch of different names. So you could find your own particular float and figure out all the information you want from your float. And you could look at it for up to 5 years. You could compare it with different floats from different people or different locations. We've been working with scientific illustrator Karen Romano-Young, who's also written a number of books, and she's created some beautiful graphics for us to help explain how the Adopt a Float program works, and I'm happy to share those with anyone. Here are some examples of a float. Here's the Rough Rider, named from Teddy Roosevelt High School. So they named it after their high school itself. This is a traveling float in the center. For some schools, we're able to take floats to the classroom and let students get a look and draw what the float actually looks like. So we'll put a transparent shell on it rather than the hard yellow casing that we have in the real floats. We now have floats adopted from a number, oops, did I skip one? I skipped a number slide, sorry. We have floats now adopted from 65 schools over 29 states and 4 different countries. We have 6 to 12 floats left to be deployed this austral season. And the neat news is that we have about 500 more floats that we have to get adopted over the next 5 years, because MBARI is almost, it's not official yet, but we put in a $50 million National Science Foundation proposal to launch 100 more floats, not just in the Southern Ocean now, but all over the world. These specific floats, they collect more data than the Argo program. But all of this together just means there's an incredible amount of data out there. And the scientists, we can't really do enough with that data. We're publishing, but we really want students all around the world to appreciate the data that's coming in, and maybe they'll find something new. Just as an example, here is the Argo float program. There are 3,909 floats that have been launched as of a couple of days ago, September 28th. Every black dot you see here is an Argo float. So we're planning on launching 500 more floats as part of this array that will now have all the biogeochemical data on them. And so we will get the data to you, and we're hoping for help from you to help get that data out to the students. And so I think that's it. I don't even know how long I took, but I tried to go relatively fast because I know it's late and I know people have dinner, but I'll take any questions that you might have. And if you'd like to adopt a float, or if you know anybody who would like to adopt a float, please email me, because we really would like to get some floats adopted.
Well, George, luckily for you, our teacher newsletter goes out soon, so we'll definitely include that in our newsletter to all of our teachers. So maybe you'll get something there. And we have a number of questions. So the first one is, do you retrieve the floats?
Great question. The answer is no. After 5 years, the floats, when their batteries run out, they sink down to the bottom. And so we've spent a lot of time working with the National Science Foundation and all the different environmental bodies talking about the potential environmental damage that these floats might cause, and it's really pretty minimal. The problem is if there is a possibility we could go get them, because we know exactly where all the floats are for the most part, but it's so expensive. Just to give you an idea, a ship day on the MBARI vessels, which mostly go from our dock out for a day and then back to our dock, that'll run you about $25,000 a day. To get on one of these larger research vessels to go down into the Southern Ocean will cost you somewhere around $80,000 to $100,000 a day. Most of those trips are 3 months in duration. And so to get a research cruise specifically to collect these floats is not an inexpensive proposition. And it's not like we really want these to be disposable. These floats cost $80,000 each. So it's not like we're just saying we're going to create these disposable floats because we can. We just think the information is that important to gather that it's worth not only the financial cost, but also the environmental cost of having to lose these floats after 5 years. But good question.
That was a good question. Another question is, I've heard of like plastic garbage patches in different parts of the ocean. Are the floats affected by the garbage, or can they detect those garbage patches?
Great question. So the garbage patches are, for the most part, not really well named because most of that garbage is not visible as a patch, not unless you have a big cluster of fishing gear or anything else like that. It's more of an accumulation of smaller particles, more like plastic soup that you might find not just at the surface, but maybe a little bit further down, just below the surface line in what we call the Newstone. So there is a lot of plastic in the ocean, but it's not going to be a barrier to something like one of these profiling floats. For us, a barrier is ice, particularly down in the Southern Ocean. And so these floats are designed, since they measure temperature, if they start coming up and they start recording temperatures below zero, freezing point of seawater is about -2 degrees Celsius. So if we start reading temperatures of zero, the float actually stops and goes back down. And it could survive, it holds on to the data. It just keeps doing this every 10 days. And it could hold on to the data for 2 years. So we have some floats that we haven't heard from in over a year, but we're not giving up on them yet because they might just be under the ice. And when the ice goes away, we're hoping that they're going to pop up and just download a whole bunch of data for us.
Awesome. So I'll ask, I'll read the whole question. How does the data get shared, charted or completely raw? Also, next one, because she added a comment, which I thought was great. My 7th grade students try to make an XY graph chart of MBARI's animal photos of how deep the animals are found, and they apparently have very much enjoyed it.
That's great. I mean, the XY charts of how deep the animals are found is great. For people who haven't seen it, we have this beautiful program called the Deepsea Guide at MBARI. And I could even share that if you want, if I could find the only thing I don't like about Zoom is when you share things, everything moves around. So let me stop sharing that, and I'm going to pull up my web page so that I could MBARI Deepsea Guide. And so now I got to share my Deepsea Guide page. And this is really a fun page. So it's just dsg.mbari.org. Or you could just Google search, which is what I did, MBARI and then Deepsea Guide. You could put in something in here, like for instance, what's a cool animal? One that we would have, let's see, blue shark. So blue shark, it recognizes that the blue shark, the scientific name is Prionace glauca. And so you could search for that. Oh, it'll tell, I'll see, that wasn't a good one because I only have one result. Oh, there we go. So here's the blue shark. It does it by taxonomy. And then the neat thing, it's got images from all, if you look for something that had multiple species, you could get all the different species or all the different genera in that taxonomy by going to the image gallery. But if you look at data products, now you get to this, which is what you were talking about. So here are all the sightings by by day of year, by depth on this axis, day of year across here. And you can see that the blue sharks are mostly found above 500 meters. And we seem to see more of them in the middle of the year, and we don't see them in the winter. That's kind of interesting. All right. Or you could look at it this way, just number of observations by depth, or what else? So there's lots of information here that you could find out, different data sets. So, or you could just download all the data and let the students graph it themselves, and you have the answer and they don't. So there's a lot of information that you could find here. Adopt a float. So if you go to adopt a float at MBARI, and you want to find out where to find the data here. So we have lots of links from the Adopt a Float program at MBARI. You find your data on the special Adopt a Float version. So here's the page I had shown a frame grab of. So for instance, if we want to find, here is a float from Seaside Middle School, and you want to plot depth on the x-axis and oxygen on the y-axis, and then here's plot, or you could do a text file. I'll do plot. You send it off, and it sits there and cranks away, and then there it is. Every time the float has gone up and down between 2000 and the surface, it's going to give you an oxygen graph. And so I probably should have flipped it, huh? Depth on that axis and oxygen. Anyway, but you could play with it, and that to me is the fun part about this program, is that there's lots of things you could do. And here are all the adopted floats. Here are all potential x variables, all the potential y variables. Or you could select your start date or your end date. So it really is kind of an interesting data site for students to start working with. And here's the interactive map of where all the floats are.
How much does it cost to adopt a float?
Oh, great question. It costs absolutely nothing. It is free. We just want you to adopt a float. Yeah, absolutely. That's a great question. And depending on the cruise, whatever's going on, we'll share all that information with you. So for instance, in this era of COVID right now, we have 4 floats that are going out on this expedition: the Icy Inverts Expedition, the Antarctic Research Expedition, and they're blogging, which is kind of fun. And so your students can read all about it. The earliest ones are down here at the bottom. And this is turning out to be a 3-month voyage for them, because they're not allowed to get on board in Punta Arenas, which is where they usually board. They have to get on the ship in San Francisco. But before they get on the ship, they have to do a 2-week quarantine. They did that. They left San Francisco. They're in Port Hueneme right now, loading up the ship. When they leave Port Hueneme, they're going to go all the way down to Punta Arenas, where they're going to reload fuel and food. And then they're going to start the Antarctic program 6 weeks after they get on board the ship. And when they're down there in the Southern Ocean, that's when they're going to deploy 4 floats that we've got adopted. But they'll be blogging the whole time, which will be kind of fun.
Okay, so another one is, I guess, what does the data contribute to? I guess just I know you guys have worked on so many projects. And I know there's so much data out there.
No, that's a great question. Why? What's the point? Why are we spending millions of dollars doing this? For the Southern Ocean in particular, it's because the Southern Ocean has been sort of a black box. We don't really know what's going on down there in terms of climate. And so one of the things we've now found with some of the data we've gathered over the last 5 years is that the Southern Ocean is actually gassing off carbon dioxide. It's not absorbing carbon dioxide like everybody thought. And that's a problem, because it's not serving as a sink for carbon dioxide. It's actually a source for carbon dioxide. So we're seeing carbon dioxide leaving the Southern Ocean in much larger amounts than anybody had predicted. So the climate change models are going to have to be adjusted a little bit. to reflect that. And that's kind of the type of data we're interested in, because the Southern Ocean is going to be one of the first bodies of water that's going to be drastically affected by climate change. Up in the Arctic is another area, right? So as all the ice starts to melt, there are things that are going to start happening, and we want to make sure we have the before picture so we know what the after picture looks like.
Thank you. Another question. So someone just wants to know if for virtual use, can they have a non-copyright close-up of the clear float?
Absolutely.
Awesome.
So that's let's see. So if you
yeah,
go,
well, I guess sorry. So they want to use the one from the website. They just want to make sure we're.
oh yeah. Absolutely. Okay. So if you get to the website, you could use anything on the website. Yeah, that's all available for you. And so, you know, here's some lesson plans that have been created. And I think that animation, that graph work was Karen Romano Young. So it's right here.
Awesome.
Yeah.
Okay, so, oh yeah, so then I guess, so how do you determine that the environment will not suffer as a result of the materials left in the ocean?
Great question. So it's mostly analysis of what type of materials we're using and the amount and the quantity of materials we're looking at. So if you look at these floats, they're really not that big. They're about 5.5 feet tall and what, 8 inches in diameter. So what they have inside are going to be some circuit boards. So there's a little bit of heavy metals. They're going to have batteries, lithium-ion batteries. So there's a little bit of damage from the batteries that are going in. But for the most part, when you look at the composition of seawater itself and the amount of metals in the seawater already, even if we lost all, you know, not only the 500 floats that we're deploying, but the 4,000 floats that Argo has already deployed, even if you lost all of those in one ocean basin, like the Pacific Ocean, because that's the one near us, you wouldn't even be able to pick it up. You wouldn't detect it. So it's not a large enough amount to really make a difference. And that's a really good question. Some of the experiments that we're doing on ocean acidification, where we're looking at what happens when the pH changes. For instance, we're trying to do this in situ, in the ocean. And so what we're doing is we're treating seawater with carbon dioxide on shore and then pumping that into the ocean. And so because we live in a marine sanctuary, a federal marine sanctuary, we had to justify what potential harm that extra carbon dioxide would do to the environment, right? Are we going to change the pH? And so the way we estimate that is we did it in scuba diver equivalents. In other words, by the time we finish our experiment, that will be the equivalent of about 300 scuba divers a year. And if you know Monterey, we could have 500 scuba divers in a day diving the breakwater. So what that does is it enables the government to take a look at the amount of damage that will result from our activities and compare it to what's already going on and really evaluate it in terms of what kind of information are you going to get for the risk of the contamination.
All right, and we'll do it, well, we're almost at the end. So one more question. So we have so many good questions today.
Sure.
What are some of the changes we should expect from the modification the ocean is undergoing?
Sure. So very good question. So sea level rise is the first one. Most of sea level rise is not necessarily from ice melting into it, from land ice melting into it. It's actually from the ocean warming. As the ocean warms up, it expands. And so we're definitely going to see sea level rise happening. And the faster the ocean warms up, the faster that will happen. As carbon dioxide in the atmosphere increases, that goes into the ocean. The carbon dioxide is causing a chemical reaction that causes the pH of the ocean to change. So we're starting to see some changes in ocean pH. We're also starting to see some changes in oxygen levels in oceans all around the world. So oxygen minimum zones, which are common all over the world, are starting to expand in how big they are. So from 100 meters thick, they're going to several hundred meters thick, and they're coming up very shallow in some regions. And that's a different issue than eutrophication, which some of your teachers and students have learned about, where you're getting so much excess nutrients from the shore, it's actually causing bacterial growth, and that's using all the oxygen. That's a whole nother issue. But these oxygen minimum zones are also creating dead zones in the world ocean.
All right, thank you. So I'm going to wrap up on the questions. Thank you so much for joining us today, George.
Oh, my pleasure.
Very much hope that I get to see you next fall.
Yeah, and if anybody didn't get their question, please feel free to email me, mage@mbari.org.